Welcome back, everybody. Today we're going to do a quick review, just a brief review on some of the global winds and how they affect ocean currents. And then we're going to get into the jet stream, which was actually part of the last lesson, but we didn't have time for it. And finally, we'll finish up with breezes today, sea breezes and land breezes. So first, let's take a look. This is the last part of your last homework assignment. And it shows surface ocean currents of the world, which is located in your reference tables. Much nicer map than this one, easier to read. And also, page 14 of your reference tables, you'll see here the global or planetary winds diagram of Earth. And the main point of all this, towards the end of that last assignment, was just to try to match up some of the global winds and see how they affect some of the surface ocean currents. And we talked about one already. I gave you an example of the Kuroshio current, and how that actually looks like it's being affected by the southwest winds. It's located in the correct spot. Here's 20 north, 40 north, and here's 30 north, 60 north, and you can see that overall the winds are coming from the southwest moving towards the northeast. Some other ones, we can see the Peru current in South America. It's moving in that direction, and that's located somewhere around maybe between the equator and just below the Tropic of Capricorn, and you'll notice it's moving kind of in this direction, kind of like over here, the southeast winds. And there's many other examples. Hopefully you guys came up with a few on the chart in the back of that homework assignment. And let me just state, though, that it's not the only thing that affects ocean currents. There's many other factors, and that's why there's currents here which are not moving the way the planetary winds move. It has to do with ocean salinity, how much salt concentrations in the water. It has to do with the fact that there's these huge things in the way called land masses, continents, which also affect which way the ocean currents flow because they hit the continents and then they get steered the other way. Just some quick questions that had to do with the last lesson on planetary winds. And here is a question from an old Regents test. The cross-section below shows different patterns of air movement in Earth's atmosphere. Air temperatures of the Earth's surface are indicated in each cross-section. Which cross-section shows the most likely pattern of air movement in Earth's atmosphere that would result from the surface air temperature shown? And you want to always recall that, the warmer the air, the easier it is going to be to rise. It's lighter, less dense. And so we have this picture for Earth's surfaces, and we have cool, warm, and cool patterns here. You can see the cool, warm, cool. And we want to look for where the air is rising, where it's warm. And so, in this first picture, it's sinking. No good. Second picture, it's rising above the warm. That looks pretty good. Let's just check the other two out. We have sinking and rising, so it's confused. And rising and sinking, so that's also confused. The best choice is choice 2. And these other choices where you see some rising air, always check out both currents before you start choosing your answers, because sometimes they're there to trick you. Okay, next question. The climate at 90 north latitude is dry because the air at that location is usually, and it says it right up there, it's dry. And what's happening here? We see air is coming around and it's sinking at 90 north. So let's look for sinking. And we see that in choices 2 and choices 4. And it's the North Pole. And air sinks at the North Pole because it's relatively cold. Cold air is going to sink compared to warm air. So the best choice would be choice 4. Hopefully you guys had that. Okay, the next question, paths of the surface planetary winds are curved due to Earth's, and we learned all about the Coriolis effect in that last lesson, and the fact that it's due to Earth's rotation, not revolution. Don't get those two things confused. So these are just typical questions you might see having to do with planetary winds. All right, jet streams. You probably heard of the jet stream. They mention this sometimes on the 6 o'clock weather forecasts. Jet streams on the Earth are easterly moving air streams. There's 2 jet streams in the northern hemisphere that are commonly found and 2 in the southern hemisphere. There are others that form different times of the year and in different places. But the 2 that we mainly talk about are the polar jet streams and the subtropical jet streams. The polar jet streams are more crucial to understanding how weather affects us here in New York State. You can see in the top view here, this is the polar jet stream. And 1,000 to 3,000 miles long, 1 to 3 miles thick. They're generally located right where the tropopause is, somewhere near the tropopause. And you can see here the equator. We have our rising air. This is a great side view of the planetary winds we learned about last time. And we know that that convection current goes to about 30 north and then sinks. And the second convection current over here also sinks at about 30 north. And this is why 30 north had that high pressure air on the ground and the low pressure at the equator, causing winds to blow from 30 north towards the equator. But back to the jet stream. This downward movement of air here and here sets up the conditions which are needed to form the subtropical jet stream, this moving river of air, I like to call it. And the same thing happens over where the air here rises. So wherever you have these divergences or convergences of these cells up at the tropopause, you're going to have these jet streams set up. Now the polar jet stream is stronger than the subtropical jet stream, mainly because the temperature differences probably it's a greater contrast, which sets up a bigger difference in conditions to make a stronger jet stream. And so that affects a lot of our weather. And the next slide here kind of talks about that. So if the jet streams move south, it generally brings colder conditions. And this is the polar jet stream. And if the jet stream moves north, it brings warmer conditions for us. And we see this all the time. Here we see the jet stream kind of flowing like that. And it goes around the planet. It's a big ring around the whole entire Earth here. And that's Wednesday at 6 a.m. Thursday at 6 a.m., you can see this little drop right here moving over this area of the country. And this is going to make it cooler there, but warmer here because it's drawing the warm air up. And let's see, on Friday at 6 a.m., you can see this major drop in the jet stream and a lot of cool air here. And relatively, I guess I should switch colors here, the warm air is stuck down there. And Saturday at 6 a.m., you can see the cool air is starting to move with the prevailing winds to the east or northeast. And looks like much warmer air in this particular setup has moved in to the western United States. So jet streams are very useful for helping meteorology forecasts. And they are pretty fast too. Another thing I didn't mention is that they're beneficial for commercial air travel. You know, when planes or jets want to fly east, they try to fly with the jet streams in them, and then if they are flying west, they want to avoid them to save fuel. All right, moving on to breezes. Now the first breeze we'll talk about is called the sea breeze. They blow from water to the land. They come from the sea and they blow towards the land in the daytime. And the reason why this happens has to do with what the difference is between when the sun comes out, the heating of land versus water. You can see over the land here, looks like a small fire or something here, but the point is that the air here over land is rising. And that's because land in the daytime heats faster than the water does. We'll learn later in the next unit about specific heats, but land heats up much quicker than seawater, and that air over the land therefore is warmer, and it's going to rise up. And as it rises, it will eventually cool off. But when it's rising, it creates this low pressure because as air rises, there's less air at the point where it started than there was before. And over the upper part here, you'll see this high pressure. I should switch colors. As the air cools off, relatively high pressure. But the main part, I guess I should switch to the other side of the picture here, is that over the water, the air is cooler. So there's a higher pressure of air over the water than the land, which causes the wind to blow, or the breeze to blow, towards the land, towards the low pressure. And this sets up a current where it's kind of drawing everything into itself. We have air moving this way, upper level wind, and then sinking, shouldn't really use red there, sinking over the water, and this convection cell setup causes what we name as a sea breeze. And you know, this is a great reason why you can fly kites at the beach reliably in the daytime. You have this breeze going on all the time. Keeps you cool too in the summertime when it's really hot. You can see the big arrows here. Now, everything switches at nighttime, because at nighttime, the land cools down faster than the water. So land, just like it heats up quickly, it cools quickly. And this causes air to want to drop over the land in the evening and in the nighttime. And this creates high pressure here. Now the water, which doesn't really change temperature very fast at all, relatively speaking, compared to the land, is going to be warmer. And that warm air will rise up, perhaps form a cloud or two, and it leaves that low pressure void there and creates a land breeze. Remember, winds are named from where they come from, so it's coming from the land, so they call it a land breeze. And this convection current continues on through the evening. This is, you know, idealized conditions. Doesn't always happen, but continues through the evening until the sun comes back up, and then this thing will stop and then reverse. And it all has to do with the fact that land heats more quickly in the daytime and cools more quickly in the nighttime than water. Water stays about even. And once again, the large arrows. And let's see if this is going to work. All right, so here we see the sun's going to set. The land's going to cool faster. Air sinks over the land, creating high pressure, and we get a land breeze. Sun comes up, land warms faster, air rises over the land, and air sinks over the ocean where it's relatively higher pressure. Play one more time. You guys watch some of the numbers here. See, the land temperature is changing much faster. The ocean temperature is staying the same at 65. And then the sun comes back up and the land heats up again. All right, hope you guys get the breeze idea. It really is a breeze if you think about it. And we're going to draw some of these and practice some more. But right now we are done for the day.